So what we're going to do in today's class, and this will blend over into Monday's class as well, is start discussions of Java Reentrant Read-Write-Lock, which has been around since Java 1.5 or so, and something new in Java 8 called a stamped lock. And in fact, when I was talking to Doug, he was telling me that they put stamped lock in because they wanted to work around some of the deficiencies that they'd found over time with Reentrant Read-Write-Lock. So before we talk about these two different mechanisms, let's first talk about readers' writer locks in general. So a reader's writer lock allows concurrent reads but exclusive writes, or exclusive write. And so what you typically have is you have this place where you can have multiple readers while other things are blocked, and then when the writers come along, all the readers have to get out of the way, and there can only be one writer at a time. There's a nice article at Wikipedia that talks about this stuff. It's often used, although not always used, in situations where you have many threads. And we'll talk about why this is the case as we go through this. If you have hardly any threads, and especially if you have data structures that don't really differentiate between readers and writers, then there isn't much point in using these locks. In fact, if the locks aren't implemented properly and or you don't use them properly, there's often not much benefit of using them at all. And so we're going to talk about that as well when we get a little further along. So here we have a shared resource like a bowl of nuts. I think those are like mixed nuts, 50% or less of peanuts. Just want to let you know that. And it allows two different models. Multiple threads can be simultaneously eating. Actually, let's say, I guess they would have to be looking at the nuts because they actually couldn't eat them, right? They could be, observing the nuts. But then if one thread wants to make a change, like add some more nuts, this metaphor falls apart very quickly, you get it, then only one thread at a time can actually write or change stuff. So I guess changing could also be eating it as well. So you can eat or add or whatever. If you're just looking at the nuts, lots of things can look at the nuts. That's the metaphor. They might help improve performance. And this is a big question mark. We're going to talk a lot more about that. Typically, they improve performance when resources are read a lot more often than they're written to. So you're predominantly reading stuff, and maybe writes happen very occasionally. And they're especially useful on processors where things can actually go concurrently. There isn't a whole lot of point in having multiple readers if you can't actually have them reading at the same time. Right? If you only have one processor and there's just one thing to do, what's the point of going to all this trouble because only one thing's going to go on at a time anyway, right? So that's some of the main issues. Now, there are also subtleties here having to do with something Doug was telling me yesterday about cache sloshing. And if you have lots of readers and part of the reading involves modifying the cache, you'll end up with all kinds of problems where the caches are sloshing around and you end up with physical layer overheads, even though you may logically appear to be doing things in a read-only way. So this sort of is a constraint on the implementation. And we'll take a look at how that works probably on Monday when we go through the implementation a bit. And if you can read more about all this stuff here in the documentation. They're tricky in practice for several reasons. Reason number one, as we talked about before, but this is even more of a problem, they can lead to read or write starvation, depending on whether readers get preference or writers get preference. Since you have a reader's writer lock, then someone has to get preference. So if a writer's there and there's a bunch of readers, does the writer get to go ahead of the readers? Or if there's writers and there's readers, do readers get to go ahead of the writers? Whichever choice you make, you can end up starving out the other thing for some period of time. 50 points to anybody who knows what this picture is. This is the starvation of Lavia refusing food. Who was Lavia, you ask? Lavia was Caligula's sister who was involved in some internal plot in ancient Rome and was sentenced to starvation. So that's her starving. So I was trying to find a picture of starvation that wasn't going to be too graphic and too disturbing. So that doesn't look too disturbing. Well, maybe it looks disturbing. That looks kind of like Voldemort, in some of the Harry Potter movies. Like maybe Goblet of Fire or something like that. Another problem is that they might actually be much, 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 much slower than other synchronizers in most use cases. If you take a look, and we'll look at some links later that point you to performance experiments with readers writer locks, you'll find that in many situations they're actually way slower than just using a Reentrant lock or a synchronizer block. So unless you're in the right circumstance, they're not going to be a win at all. And then the third thing, which I should put in here, is fixing these problems, which is what StampedLocks do, are also more complicated to program, which we'll see later. Yes, sir?
Have you seen the revision of this with the bent iPhones?
No, that's hilarious. That's great. I think there's also a Bugs or like Bugs Bunny or thing where it's the Roadrunner's melted or the Coyote. There's other things like that as well. So what's an example of human known use? Well, this is quasi-human known and quasi-propeller head, our world. Imagine you run the website for Vanderbilt where certain content changes, but very, very infrequently, like the course catalog. Right? The course catalog probably gets updated once a year before they put out the next version of the courses. Right? So it does get updated, but 99.999% of the time, you're just read-only access to content. So a reader's writer protocol in real life would be, how do they go about updating the website, right? So what they're going to do, of course, is most of the time, it's just a read-only thing, and you don't really need to lock anything. But every so often, you've got to come along and grab that lock and update the content. And during that time, at least in theory, you don't want people to sort of get half of one document and half of another. Or at least you don't want your data structures corrupted. So that's sort of a quasi-human known use. OK, so let's talk, now that we've talked a bit about sort of the overall view of what a reader's writer lock is, let's talk about Reentrant read-write locks. So Reentrant read-write locks are a Java class that implements the read-write lock interface. So there's an interface that gives the key mechanisms, key methods, and you'll see it's a very, very simple interface. And it actually uses the lock interface, so there's a dependency going on there. And you can find out all the goodies about what this thing does by reading here. Here's what it actually looks like. So Reentrant read-write lock implements read-write lock, and it then has a couple of data members, one called reader lock, one called writer lock, and reader lock and writer lock are instances of read lock and write lock, which are nested classes, which we'll probably have time to look at next class. We'll go through the implementation in more detail. But in a nutshell, these guys implement the lock interface. So if you already know what lock is, which you would know from Reentrant lock, then a read lock or a write lock is just like a lock in the sense it has lock and unlock and try lock and all that kind of good stuff. OK, so that's kind of how that works. The rules are that while you have the read lock held, while the read lock is held, any writers that want to come along have got to queue up and wait, and a bunch of readers can run as long as they own the read lock. Now here's where things get tricky in terms of who gets preference, readers or writers, right? If another reader comes along, does it get to jump into this queue, or does it have to wait till the write lock goes? That's where the whole starvation issue and liveness issue comes in. But the rule is if you're got the read lock held, readers can read. But when the write lock is held, only one writer can be in the critical section. Any other writers have got to be queued up. Any other readers have got to be queued up, one write at a time. Now, there's an interesting design issue here that is, how do you know how to decompose your system according to reads and writes? And when we look at some examples, we'll look at that in a little bit more detail. Under the hood, just like everything else, or not everything else, a lot of the stuff we're going to look at, the implementation of Reentrant read-write lock uses the bridge pattern, which we've seen before. It is almost identical to the one we had before for Reentrant lock, except this is a Reentrant read-write lock. And as you can see, one of the consequences of this is fair sync is way slower than non-fair sync, which is pretty slow also, but be careful with those things. It uses the abstract queued synchronizer. We'll talk about that next time. This is just review. This is stuff you already know. That it makes the choice using the bridge pattern. And then here's the part I want to show you. So in the constructor, it goes ahead and allocates a read lock and a write lock, and it stashes these things away in data members. And then these data members can be accessed via accessor methods. So the actual methods on ReentrantReadWriteLock are really just read lock and write lock. And those are just accessors that return the references to the underlying read lock and write lock. So the interface is actually kind of boring, right? It just give me the reader, give me the writer. And those guys themselves, of course, are implemented, and we'll look at those implementations later. So applications grab these things, and then they go ahead and use them, and they lock and unlock them. And that's where the magic happens. Now, as we see when we look at the implementation, write lock and read lock, these guys, these classes here, they use the shared mode of abstract queued synchronizer. So when we looked at abstract queued synchronizer, remember the framework we looked at last time that we used for reentrant lock? We looked at the exclusive mode there, because exclusive mode is what's used to give exclusive access. They also support shared mode, and shared mode is what allows them to be able to support readers and a writer model. So we'll look at that in more detail when we go through the code. Now, there's also a bunch of properties that are supported here. So there's reentrancy, just like you have for the reentrant lock. There's this very interesting thing called lock downgrading, which we're going to look at, which is completely insane. It should be called lock degrading, because it's very degrading to have to figure out how it works, but I'll show you how it works. Interruption of lock acquisition, which is interrupted locks, just like we've seen before. And then there's also support for condition implementations. Now, when I talked to Doug, he said one reason why this stuff is slow is because these were the requirements for the interface. So it forced an implementation that could not be optimized. So for example, not allowing reentrancy speeds things up a lot, because you can do more work in hardware. If you allow reentrancy, more of the work has to be done in software, and so on and so forth. OK, so now let's take a look at a bunch of different ways of using read-write locks. Now, you've seen some of this stuff already, because we went through the simple atomic long example. I'm going to look at that one again, but I'm going to look at it for a slightly different reason this time. Other stuff you really haven't seen, and it's interesting to know some reasons why people use read-write locks, which are sometimes a little surprising. In fact, the two main uses I was able to find of these things in Android and Java, and by the way, there are two known uses in the whole thing. They were both using for the same basic purpose, which I found rather interesting. So let's talk about that. So one implementation was in Bluetooth socket. A socket is a communication mechanism, and a Bluetooth socket is used to communicate between your Bluetooth device and your phone, which is a Bluetooth server. So Bluetooth socket, it has a method called close, which is used to close down the socket. Okay. And here's what it looks like. A Bluetooth socket implements the closable interface, which gives it the close method. And we're just going to look at the parts that are sort of sticking above the water. We're not going to look at all the details of how this works, because it's not important, really. So here's what it looks like. You could have a bunch of threads running, and at some point, those threads decide they want to close down the Bluetooth socket. Now, keep in mind, other threads could be doing other things. They could be reading from the Bluetooth socket. They could be writing to the Bluetooth socket. They can be closing it, etc. So there's a bunch of threads running along. And to make this work, we're going to make ourselves a reentrant read-write lock. And then here's the close method. Now, the way it works is it's perfectly OK to have multiple threads call close, because you really don't have an easy way to control that otherwise. And the way it works under the hood is that the first thread that calls close will actually close it, and any other thread that calls after the first thread closes it will find that it's closed and will just go ahead and return. Right? So you have to have some way to protect yourself. And what's interesting is this example and the other example we're about to look at, that's from the Sun implementation of asynchronous server socket mechanisms in the Java new I/O package, are both using things in much the same way. So there's a common pattern going on here. So what happens here is when you come into close, the first thing you do is you acquire the lock for reading. So you could have a bunch of readers that are all going through this piece of the code. And if we were to look at the code, we would see that this piece of code here in the try block checks to see if the socket has already been closed. And if it has been, it just bails out. It just returns. And then it goes ahead and unlocks the lock. Okay? the first time in other words, before it's been closed, it hasn't been closed. So we'll grab a read lock, and then let's say 5 threads show up simultaneously on close. One of them will then get through the write lock. This is the same lock. We now acquire the lock for writing. And then what we're going to do is we're going to go ahead and, with the write lock held, which means we have exclusive access, we're then going to go ahead and close the socket and release the resources, and then we'll release the write lock. So when the other threads get in here, they're going to find that it's been closed down. Yeah, Jake?
Does that mean the read lock or the write lock's nested inside of the read lock?
No. If you look back up here, I sort of skipped that part to make it a little easier to see. But this code here is right there.
Okay.
So we come in, we acquire the read lock. If we've been shut down, we bail out and never acquire the write lock. So many threads will most likely grab a read lock and just bail out, no write lock acquired. So many threads can quickly shut themselves down. One thread will come through and actually close down the store, but just one. OK, so multiple threads can acquire the lock for reading, but only one thread at a time can acquire the lock for writing. Pretty cool. All right, so now let's take a look at yet a different example, but it's the same idea. This is from this mouthful of a class, Asynchronous Server Socket Channel Impl, which is part of the new I/O implementation. That's Sun's implementation of Java. So Sun has re-implemented something in a more efficient way. God knows why, but there's a generic version for all operating systems that does not use this technique, and then Sun has a version that works on their platform. And here's basically what happens. And in fact, I'm going to jump over here and show you the code for this, because it's easier to see it that way. Or put another way, I haven't had a chance to integrate it into my stuff yet. Oh, yeah. All right, give me a second. Yeah, this is very, very calming, isn't it? No, that isn't very calming this time. No, is it? Usually it's very calming. It's like
when you're on hold.
OK, so here's asynchronous server socket channel impl. All right, so take a look at this. So you can see we have a couple things. We have a descriptor, which is connected to a socket, and some other stuff. Here's the non-intrinsic lock, Jonathan. It's an extrinsic lock, but it's a lock. Here is the read-write lock. Notice how the read-write lock is an interface. It's an instance of an interface that's implemented by the implementation. And we have a flag that keeps track of whether we're open or not. And if you come down here, you will see that we have a method called begin and end. And what begin does is it acquires a lock for reading, and it checks to see if it's open. And if it's no longer open, it bails out by throwing an exception. And when end is called, it unlocks the lock. So those are begin and end. Those are the read locks. This is very similar to the Bluetooth socket close method. Here is the close method for this thing. As you can see, very much like the other example, close method acquires the lock for writing and then sets the lock, sets the flag to indicate we're closed. So we're no longer open. Open equals false. And then we release the lock. So this guy actually acquires the lock and changes the state. That's the key difference, by the way. The ones that acquire the write lock have to change the state, and the ones that acquire the read lock don't. And then if you come down here and you look for uses of begin end, you'll see begin end work on regions of code where read operations are being done on internal state that doesn't change but need to be protected in case we're closing down. So all the access to the file descriptors here, these things would be in trouble if we unilaterally shut ourselves down. So we grab the read lock, do a bunch of work, and then however we leave this thing, we end to release the lock. And there's a couple other cases like that. There's a bunch of cases where we do begin. Notice how we're doing a socket option, another socket option. So there's a bunch of different things we do here where we begin the read section and stuff takes place. So the basic idea here is that we're holding read locks for regions where we're not making changes to the state, but then when we close down, we go ahead and grab the write lock and close ourselves down. So that's another use of Reentrant Read-Write Lock. Yes, sir, Colin.
Do you think they were both used for similar purposes? one got the idea from the other, or that it's just a good idiom to use in that case?
I think it's an idiom that gets used occasionally, you know, and it really has to do with the following. There's a bunch of threads that are doing stuff, and much like the example I gave with updating the course catalog on the website, you know, it doesn't change very much. You don't close down a whole lot. You're mostly open, and then once in a while you close down. But when you close down, you have to close down in an orderly way. Just like you don't often update the content of the course catalog, but when you do, you want to do it in an orderly way. So they use the read locks to give you pretty much unfettered access of many threads to the state of the object that isn't changing very much. But then when something's going to change, in this case when you shut down, we have to grab a write lock to give ourselves exclusive access. So that's basically the idea. And that is the same idea for all these examples. It's just funny how it was used for close, you know, in those cases. All right, here's another example. This is one we've seen before, but I want to show you something a little different. This is the simple atomic long. You've seen this one already. This is the one where we cache the results. And the real implementation uses compare and swap, but I'm really setting this up to show you the compare and swap implementation in a second. So you've already seen this implementation. We don't need to use fair semantics for this guy. We use the try finally idiom. This is grabbing a read lock. Oh, by the way, here's a quiz question for you. Well, I'll tell you. I'll wait till we get to the atomic long, the real implementation. Notice that this particular version grabs the lock, the read lock. And then here's the write lock. We grab the lock, do the work, and then release it. Now, I'm not going to show you this implementation here because I want to wait till I show you the next piece. This is an example of lock downgrading. Or actually, I will walk through it very quickly. This will blow your mind. So Reentrant read-write-lock support the idea of lock downgrading. They don't support the idea of lock upgrading. Stamped locks do support lock upgrading. What is lock upgrading and lock downgrading? If you own a write lock and you don't want to own the write lock anymore, but you don't want to entirely release the lock altogether, you can downgrade to a read lock. Conversely, which is not supported by Reentrant read-write-lock, but in stamped lock it is, if you own a read lock and you get to a point where you want to write, you can try to convert yourself to a write lock, which is an upgrade, right? You're upgrading. You have more power. And then when you downgrade, you have less power. Jake?
Does that upgrade guarantee that no one will have written between?
That's why it's called try. We'll see some examples of this when we look at stamp locks. It's very subtle. So here's an example of using lock downgrading with Reentrant read-write-lock. So we come in here. This is the increment and get method. So increment and get has some stuff where we're going to be doing, we're going to read, and some stuff where we're going to write. So we might want to differentiate those two things. So we come in here and we first grab the write lock, okay, and then we lock it. The lock is held. So this thing is done in a mutually exclusive way. We've incremented the count, right? We then go ahead and we get a new lock, which is the read lock portion of the read-write lock. And then we go ahead and we lock the read lock. This is the downgrading part. So now we've got the write lock held and we've got the read lock held. And then we unlock the write lock. So because we have the read lock held, the lock has not entirely been removed altogether, but we've downgraded from a write lock to a read lock. And the reason we're doing this is because then this call here, where we're going to read the current value and then eventually return it, that doesn't have to be done with the write lock held. Reading the value doesn't require a write lock. But we never released the whole thing entirely. We just downgraded it. And then we do a little sleight of hand. We set, since we released the write lock here, we set lock to read lock. And then we go ahead and we unlock whatever the lock was. So depending on various things, this will either be unlocking the read lock or it will be unlocking the write lock. But in either case, it gets unlocked. So that's the protocol for doing this. It's wacky. You can read about it here. There's an explanation of why it does this. Lawrence?
There's a ton of pointers going on there in the underlying implementation.
Well, they're Java references, blah, 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 which are not quite pointers. What was your concern?
Oh no, I was just thinking about. I I was just thinking about how it was swapping references around.
Oh yeah, in Java makes that seamless and easy and good. Colin?
So I know we had mentioned before that you can't acquire read lock to write lock cell. Are we able to do that in this case because it's reentrant?
Well, let's see. We acquire it, but it doesn't do us any good until we release the write lock. But we acquire it. I mean, in other words, when you have a read lock, grabbing when you have a write lock, grabbing the read lock doesn't do you any good, right? It doesn't help you. It's already locked.
So does the Reentrant read-write lock allow the same thread to grab a read lock?
Yes.
So it needs to be a Reentrant read-write.
And by default, they are reentrant.
Right.
This implementation is reentrant. Okay, so now what I want to show you is just go over here. Let's go take a look just for kicks. Oh, yeah. Let's go take a look at, that's much more pleasing, isn't it? Very, very pleasant. Okay, here is atomic long. All right, so this is how they actually do the atomic long implementation. I showed you the reader's writer lock version, which is bad for a lot of reasons. I just wanted to show you reader's writer locks. But here is atomic long. It grabs the unsafe object, and it grabs this funky thing called the value offset. That's a fascinating idiom. You see it used all over the place at this level. And then what they do is they use Java reflection to go grab the value field, which is defined here. They go grab this by reflection and figure out how far away is this in bytes from the beginning of the object. And that is what's called the value offset. And that's used by the atomic concurrent swap operation to check a region of memory to see if it's 0 or 1. It's really cool. You'll see it in a second. Here's the actual value. Now, this is what I was asking before. So this thing is volatile. So it's private volatile long. And if you go take a look here, you'll see the get operation returns the volatile value. There's no read lock there, right? Now, the question for you is, what's the difference between a volatile used like this versus using the read lock? Are those equivalent? Nathan?
Wouldn't you still be able to access the volatile even if a write lock is required?
Exactly. Thank you. That's exactly the point. So if you use a read lock, lots of readers can be simultaneously reading. But if someone else owns the write lock, then you have to wait. Whereas with volatile, if someone reads a volatile variable, it doesn't matter if the write lock is locked or not, it's going to read it. That's kind of interesting, right? Now, the only reason that works is because volatile has these semantics for doing all or nothing assignment. Think of volatile as like synchronized for data, for a piece of data, right? That's what volatile is. So that's kind of subtle, but it indicates why you see this idiom used all over the place. The real heavy lifting gets done down here. Here's, for example, here's get and increment. So if you were to take a peek in the unsafe class, you'd see there's a method called get and add long. And here's what get and add long does. It has a local variable called v, and it goes into a while loop, and it goes ahead and it takes the object, which in this case is this, and it adds the offset to it, which we computed from before. This is going to go ahead and grab the appropriate offset to get the variable that we want, which in this case is going to be the value of the atomic long. It grabs that thing, and then we do a compare and swap operation. Compare and swap long takes the object and the offset, goes to that location and says, does it have the value v, which it should, because that's what its value was. And if it has the value v, replace it with v plus delta. So what that's doing is that's basically adding this to the current value. So if this guy has this value, we add that thing to it, and then we return its old value. So its old value comes back. And so what happens here is we get an increment. So that's going to add 1, or add whatever, in this case 1. It's going to add 1, but it's going to return the old value. And it does that atomically. And then down here, here's increment and get, which increments it first and then returns the incremented value, right? And that calls get, add, and long. Except what it does in this case, it's totally funky. It adds 1 to the value, but it will have returned the old value down here, so it adds 1 to it. But it will have been updated already, right? So these are using these super duper optimized hardware level instructions to manipulate what's going on. And that's why it's very fast. Now, having said that, there's something new in Java 8 called long adders, which are even faster under certain circumstances. Yeah?
So value offset, so the whole point of that is that just pushes it?
No, what it's doing is it's a complete and utter hack, but it's very clever. Keep in mind, this is Java, so there's probably a bunch of other things that are part of the object in addition to its fields, like there's probably a v pointer and all that kind of good stuff. And so here is, private long value. That's the thing that we want to be able to check to set its value atomically, right? We want that to be incremented or decremented atomically. So that's not at location 0 in the object. That's in location, whatever get declared field value gives you back, like location 4. Let's say it's 4 bytes into the object. So what that's doing is that's getting under the hood. It's getting a pointer to that location offset from the beginning of the object. And so when we do compare and set, we're taking the beginning of the object, adding the offset, and then we're going into that physical piece of memory, and compare and set is checking that particular piece of memory to see what its value is.
Isn't that because compare and set needs the actual address?
It needs the actual address.
Oh, okay.
Exactly. Yeah, it needs a memory location.
Right.
Yeah.
So it's a private member variable there, and we're accessing it from wherever. That doesn't break anything or break encapsulation or just.
We're not accessing it from wherever. We're accessing it from the implementation of the class. And that perhaps is why the word unsafe is the qualifier here, right? These are not things that you're allowed to do unless you are like a 6-degree black belt in Java, right? But yes, there used to be this strange phrase during the Vietnam War that said we had to destroy the village in order to save it, right? So this is a good example of having to break the abstraction in order to preserve it, right? We have to break some abstractions in order to be able to preserve abstractions. So that's kind of the idea. Been trying to figure out a way to work that metaphor in, and I finally found one. If you recall, we left off before talking about Reentrant Read-Write Lock. And I talked about what a Reentrant Read-Write Lock was in general. We talked about how Reentrant Read-Write Lock works in Java. It inherits the read-write lock interface and provides the methods that are exposed to there, which basically give you factories to get the readers and get the writers, and then you can do lock and unlock on those objects, sort of sub-objects, if you will. Fairly straightforward interface to use, not all that complicated. And I talked about a couple of different examples that used it, including things like we used it to implement the atomic long operation to be able to give readers, multiple readers threads, access to the lock, to the long value, but only let one writer at a time go in and actually make the change. And if you recall, we talked about sort of how it was done in the real Java implementation. We talked about how simple, or how atomic long was done in a real Java implementation, where it used basically compare and set operations, and it used volatile count and so on. And we talked about some of the downsides with using Reentrant Read-Write Lock. So what we're going to do now is we're going to expand the discussion of Reentrant Read-Write Lock's usage considerations. So the idea of read-write lock is to enable greater concurrency when accessing shared data relative to other kinds of synchronizers, like Reentrant lock or the synchronized keyword, synchronized block, synchronized method, and so on. So that's the idea behind this. And if you take a look here, it gives you some details about when this stuff actually makes sense, and we'll talk about that. The thing to remember, though, is that in practice, these speed-ups may not necessarily materialize. So as the Environmental Protection Agency always says when they give you gasoline mile per gallon counts on car stickers, your mileage may vary, right? So the only way to really do this is to sit down and do some benchmarking. So here are some conditions under which you might achieve the benefits of read-write locks relative to the earlier forms of synchronizers we talked about. So one thing is, to some extent, that whether they're a win or not depends on the frequency with which readers and writers occur. So ideally, you'd like to have a scenario where you have a lot more readers than writers. Remember we used the example last time about the Vanderbilt course catalog where it gets updated like once a year, but otherwise you're just reading it. So that's an example where there's lots and lots more readers than there are writers. Writing happens once in a blue moon. Obviously, more fine-grained data structures have more writers. Another issue is the duration of read and write operations. So if your read operations are very, very short, if you acquire a lock and you read for a nanosecond and then you release the lock, that's probably not going to give you much of a win because the locking overhead itself will be more expensive than the amount of things that you're actually protecting during the read. So reader-writer locks work best if you spend several thousand instructions doing something once you've acquired the read lock, because then the cost of the locking becomes in the noise and more stuff is actually running in parallel, right? Because you acquire the lock, you pay whatever overhead you pay for that, and then you have a while to run concurrently before you have to go ahead and give up the lock. But that, not all data structures work that way, so that's the ideal situation. There's also the whole issue of contention for the data. You'd like to have, what contention means, at any given point in time, how many things are simultaneously trying to access the state that's being either accessed exclusively or shared. And ideally, again, you'd like to have lots of concurrent readers at the same time. That's where you're going to get the biggest win from this stuff. And then also the other issue is the number of cores. So if you only have one core or one CPU with a single core, readers, writers aren't going to give you much of a win because they aren't going to be able to do things concurrently. So ideally, you'd like to have many cores. So those are sort of the ideal circumstances under which you'd like this stuff to occur. Often, however, for a variety of reasons, which we'll talk a little bit about as we get into the next subject, Reentrant read-write locks are often more expensive, and in fact, sometimes way more expensive than other mechanisms. In fact, oftentimes, and in fact, most of the time, you'll see that Reentrant read-write locks are actually much slower than just using a synchronized block, which is kind of weird, if you think about it. So what happened here, they created an abstraction that looked good in the abstract, but when actually applied in most normal use cases was way less efficient than just grabbing a lock, just grabbing a synchronized block, which doesn't differentiate between readers and writers. And I'll show you some benchmark stuff. So there's a bunch of issues, there's a bunch of problems. Let's talk a little bit about them. There's a really nice article here. If you go to this link, you can find a really nice article that does a lot of benchmarking, and it talks about some of the issues and compares and contrasts the different approaches. So one of the problems with Reentrant read-write lock is that both read and write locks are so-called pessimistic. And you all know what this is, right? Is the glass half empty or half full, right? So it turns out that in reader-writer locks, Reentrant read-write locks in Java, both things are pessimistic. And what that means is that you have to acquire the lock in order to be able to make progress on stuff. So the lock has to be held. Whether it be a read lock, whether it be a write lock, you have to have the lock. Now, at first you might think, well, yeah, but what else the heck are you going to do? You got to do something, right? Well, that's what we're going to talk about in a second. We're going to talk about another variant that's been added in Java 8 called a stamped lock that allows us to be optimistic. And we'll see that there are situations where that can be a huge win. So the two things to compare this with are stamped lock, which we'll talk about in a second, as well as with volatile. Remember, volatile allowed you to really have simultaneous readers, even if writers were taking place, because of the semantics of volatile. Another problem that you have with Reentrant read-write lock is that you can end up starving either the readers or the writers, depending on their priority. And this is discussed, the issue of starvation is discussed here. Let's see. So basically what happens here is that earlier versions of Java 5, which was where they first introduced this stuff, they gave preference to readers, which meant if there were lots of readers, the writers got starved, and people realized that was kind of a problem. So then in Java 6, oops, it's not witters, it's writers. Java 6 and beyond, and henceforth, writers get preference, But of course, you're just robbing Peter to pay Paul. Now, writers get a chance to go, but if writers never stop, readers get starved out for an indefinite period of time. This issue of starvation is just a common problem in these types of abstractions. And there's a real nice discussion about starvation issues here in this article. And then the other problem you have with them, now this is all, of course, relative to, what is this relative to? They can be tedious and error-prone to program, in much the same way that Reentrant locks can be tedious and error-prone to program, because you forget to acquire the lock, or you forget to release the lock, or you hold the lock too long, you don't hold the lock at all, all those kind of things. Those are common problems. Compared with synchronized blocks or synchronized methods, where you just put synchronized and it's all taken care of for you by the magic of the scoped locking idiom, or the resource acquisition is assignment is initialization kinds of things. So it can be tedious and error-prone to program relative to synchronized. Yeah?
So in these cases, I know you mentioned a couple times now about forgetting to acquire the lock. Can you
Yeah.
actually change state without acquiring the lock if you forget to?
Oh, sure. Sure. How many times has this ever happened to you? You've gone into a restroom with a lock on the door and you forgot to lock it, and somebody walks in, right? I mean, that doesn't happen a lot, but it happens, and you're like, oh man, I forgot to lock the door, So yeah, there's nothing. The whole thing is up to you to do it right? So in these kinds of locking mechanisms, they expect the programmer knows what they're doing. Now, there's ways around that by programming at much higher levels of abstraction, and we'll talk about some of those later, where a lot of the locking issues kind of go away, or you partition your data sets in such a way that locks are unnecessary because they're embarrassingly parallel.
And of course, with what he was saying, wouldn't that be more like if they don't try to acquire the lock, then they would just walk through the door, whether it's locked or not. So somebody else locks it, but if you don't try to acquire it, then you just walk right through.
Right.
Somehow.
Yeah. It's kind of like
Paranormal.
like the paranormal or the Marvel villain Juggernaut, who just smashes things down, something like that. Yeah. So obviously, if you don't acquire the locks, you may think you're getting ahead of you're like getting ahead, but you're actually reading stuff that is absolutely nonsensical, right? So it doesn't really help you. Okay, another important thing to remember here, and this is true no matter what you do with concurrency as a rule, and probably more generally with computer programming, if performance matters, you've got to actually profile the results. You've got to figure out, based on measurement, which ones make a difference. And I'll show you some measurements here in a second to give you a flavor for this. There's a nice article here that talks about a pattern language for picking which locks are best under what circumstances. So that's kind of a good thing. This is a more general discussion of locking, not just Java locks, but it's good to have this kind of knowledge. Now, we'll talk about benchmarking in a second. I'll show you some examples. What is the downside with benchmarking? Can anybody think about, so you want to use benchmarking to give you some ideas of how things, quote, really work. But there's also a downside to that. Can anybody think of what a downside might be to using benchmarking?
We can't necessarily test all cases.
Right, so you can't test all cases. In particular, if the workstation or laptop you're doing your testing on is not representative of where you're actually going to deploy and run the real system, you may come up with results that have nothing whatsoever to do with the actual experience. And that happens all the time, right? If people are trying to build something that's going to run in the cloud with hundreds of thousands of concurrent users, and they have like a laptop with one core, and they're making all their decisions about how to design their locking strategy based on that environment, it's unlikely it's going to match the real world. So that's part of the problem. These things are also heavily based on the assumptions of access or load or usage patterns, right? So if you don't get that just right, you again can fool yourself into thinking you understand what the results are without really having a deep understanding. So that's the typical problem with benchmarking. But it's better to benchmark than not to benchmark, usually. So here, this is good locking primitives for parallel programs. Definitely take a look at this, and they talk about different kinds of locking and so on. All right, so this is what a Reentrant read-write lock looks like. We're not going to look at the code today. We'll probably look at the code on Wednesday. It's substantially more complicated than the code that was there for Reentrant lock that we looked at already. And you can just look at this to kind of get a feeling for why that is, right? So here's the actual class itself. And this includes some of the non-public interfaces as well. But this gives you sort of a sense of what the external world sees. And then internally, they use a sync class with the bridge pattern like we've seen before. And under the hood, this thing, of course, inherits. This isn't even actually showing all the complexity. This isn't showing the relationship to abstract queued synchronizer, which is lurking here. And you have non-fair sync and fair sync, which are basically, inheriting from the lock interface. And they also have this interesting stuff that they put off to the side. They call the hold counter, which is used for reentrancy, because Java reentrant read-write locks are reentrant, as the name might imply, which is one of the things that makes them inefficient, because they had to support those abstractions efficiently without doing cache sloshing and so on. So this just gives you a sense of the complexity of what's going on. Keep that in mind. We'll come back and look at this a little bit later. All right, so let's now that you have some idea of what a reader's writer lock is in general, and you see one attempt at trying to implement them in Java as a reusable library, now we're going to talk about another later way of trying to fix the problems with the earlier version. Done by the same person, largely, with Doug Lee, with some help from his colleagues. And the idea is to have something that will give you faster reader's writer semantics than we had with Java Reentrant read-write lock. And here's the thing. StampedLock is its name. So if Reentrant read-write lock is kind of this clunky, older vehicle that isn't really souped up and optimized, StampedLock is meant to be much faster, much more tuned for performance, that kind of stuff. You can see the that's the same thing. Okay, so here's what things look like. You can go if you get yourself access to the Java 8 source code, you can find the implementation here. We will look at the implementation later, probably next time. Right now, I just want to give you a flavor for what the interface is like. So StampedLock is a class that implements Java I/O serializable. Now, what's interesting about this is, unlike Reentrant read-write lock, this does not implement the read-write lock interface, does not use abstract queued synchronizer, and does not apply the bridge pattern. So it really strips out a lot of the stuff that was causing Reentrant read-write lock to be slower and not to scale very well. So, for example, they don't have reentrancy. They don't use any of the stuff that came out of abstract queued synchronizer. And they have a different interface than read-write lock. And they don't differentiate between fair and non-fair semantics. So those are some things that they do. And as a result, things can be a lot faster. Instead, they provide 3 locking modes: writing, reading, and optimistic reading. So we're going to talk about all 3 of those. So the first locking mode is writing, and this is basically the exclusive mode, right? So if you think about, with a regular synchronizer, like a synchronized block or synchronized method or a Reentrant lock, those are exclusive locks, as one at a time holds them. So with a stamped lock, you can create it in so-called exclusive mode. And one way to do it is to call the write lock method, and write lock will block until it can get a write lock. And so it gives back a lock that's an exclusive lock. Only one thread can be going through, can own this lock at a time. And what write lock gives you back is it gives you back a long, which is something called a stamp. And when we look at the implementation, you'll see a stamp is basically keeps track of a version and in the state, like what mode it's in, and this generation count. You'll see what that means later. There's also something called try write lock, which tries to acquire the lock if it's available right away. If it is available right away, like if you were trying to get a write lock and it's available, then it will go ahead and return to you a valid stamp. If you call try write lock and the write lock is not immediately available, it will return 0, which said I tried, I couldn't get it. So it's basically a non-blocking attempt to try to get yourself a write lock. And then the final thing we have is try write lock, where we give time units and we say wait up to this amount of time to get the lock. And if you get it in this amount of time, good, you get back a valid stamp. If you don't, you get back a 0. Okay? So those are the three things. The next modes are reading. And once again, we have something called read lock, which will return to you a valid stamp, blocking if necessary, until it can get a read. It can get the lock in read mode. Now, if there's already writers in the queue, then you'll have to wait, right? Because you have to wait for the writers to be finished and release the lock before you can become a reader. So calling read lock will block until you can acquire the lock. And if you get it, you get back a stamp that says I'm a valid read lock. As before, you have non-exclusive attempt at trying to get a read lock, and you also have a timed attempt at trying to get a read lock. Same basic ideas as before. Okay, so far so good. So far, it's pretty much more or less just like Reentrant read-write-lock, and there's a few little tweaks. Here's where things get interesting. So the third mode is the so-called optimistic reading mode. And I should also point out, if you look at the implementation of the read lock and write lock, those things typically have to actually do something. They actually acquire locks, right? So there's some overhead, either they're spinning or queuing or that kind of stuff. Optimistic reading is a little different. This is the thing that differentiates StampedLock from Reentrant read-write-lock. What optimistic reading does is it has a method called try optimistic read. And this thing basically doesn't do much of anything other than set some flags in the stamp that gets returned back to the caller. And it just kind of marks and says, I'm trying to acquire this thing in optimistic read-write mode. But it doesn't acquire any locks. It doesn't do anything funky at all. It just gives you back a stamp that's been marked. And that's what's called an observation stamp. We'll see that more later. Or, actually, if the lock is available, then you get it, right? You get a read lock. But it gives you, so I'm sorry, it'll fail if it's locked exclusively because it's a try optimistic read. Now, once you get try optimistic read, you now can go ahead and read the data. And the way you do it is you always read the data into local data members. So remember, what we're doing is we're reading from an object that has so-called shared mutable state. What does mutable state mean? It can change, and you have to be careful. The minute you have shared mutable state, then you have to worry about multiple threads changing the state in inconsistent ways. By the way, just out of curiosity, does anybody know what the opposite of mutable state is? Immutable state. There's actually a paradigm for locking in Java where every time you do an operation that might change something, instead of grabbing a lock, you make a new object with that value. That's called immutable objects, and they are by definition thread safe. The problem is that you have a gazillion objects, which makes your garbage collector tend to fall over from the strain. So it's not really a realistic solution, although it is used in some places. The time and date class in Java 8 apparently uses immutable objects now. Okay, so you get back the stamp. Let's assume, well, actually, usually what you do is you get back a stamp. You could check to see whether you got a 0 or a non-zero, but usually what you do is you get back a stamp, you assume it wasn't 0, and then you go ahead and you take the values, which are usually data members from an object, and you store them in local variables in the runtime stack of the calling thread, the thread that called try acquire. Why do you do that? What's the purpose of storing the mutable state in local variables? Jeffrey?
So that if it isn't validated, you aren't corrupting someone else's data, just your own data.
Right. So remember, local variables are always thread safe. Nobody can get to them. It's only your thread, and they're local in the thread of the stack. So I mean, unless you do something completely bizarre, like grab this thing and take its address and store it in a global variable, which I don't think you can really even do in Java unless you use unsafed operations. So you're pretty darn safe that these things are not going to be tampered with by another thread. So you stick them into a local variable. And then once you're done reading them, and by the way, you don't want to be reading for a long period of time. You want to keep this read window very short, very small. What you then do is you go ahead and you call the validate method, passing in the stamp that came back from try optimistic read. And if the stamp that comes back, if it turns out nobody has come along and acquired the lock exclusively between the time you got the optimistic read and the time you validated it, you're golden, right? So what that meant was, you actually did this and nobody came along and could have changed things. Again, assuming that they're following the protocol, of course. So if that happened, you now have the values. You have read those values into local variables, and now you can use those local variables because you had a snapshot of their consistent value without having anybody come along and acquire for writing and then overwritten them. And that's another reason you store them in local variables, because once you've read them, they're still valid. Now, here's the thing to remember about modern processor architectures with cores and memory and mutable state and so on. They're always lying to you. So if you have a list or a queue that's a synchronized list or queue, and you ask the thing, how big are you? They will give you the best approximation they can at the time that they return from that call. But the second you get the result back, it may have changed. Right? So they're always lying to you. However, in this particular case, we did get a snapshot of the values at a point in time, and they have not changed. I mean, they cannot be changed because we stashed them into local variables. So we've got them for that moment. That was the valid values, right? And somebody else is also, so basically, we're OK at that point. We got a snapshot that has not been corrupted. Now, the last thing that happens in validate, and we'll see this when we look at it, is they use a memory fence operation to basically go ahead and sort of push the values out, the red values out, so everybody has a consistent view. And when we look at the implementation, we'll look at that in a little bit more detail. So the good news here is if validate succeeds, synchronization overhead is really low because you didn't really do anything. You haven't grabbed a lock. You may have done a little cache stuff with cache lines, but you have not acquired a lock. So things are going to be very fast. Now, as you might anticipate when we get to the example where I show you the code for all this stuff, it's much more complicated than doing reentrant read-write locks. So there's a different set of patterns at play, or idioms. OK, so this is the real secret sauce of stamped lock, is the try, optimistic read, and validate. Now, there's also methods that do some other stuff. They convert across lock modes. So for example, try to convert to write lock takes a stamp, and if the lock state matches the stamp, then several actions, one action of the following happens. If the stamp is a write lock, then we return it, because you try to convert to a write lock. It's already a write lock. You're done, right? You got a write lock. That's good. If it's a read lock, then if the current state is a read lock, if the stamp is a read lock stamp and the write lock is available, atomically release the read lock and return a write stamp. So sort of upgrade it. So this is sort of an example of a lock upgrade. Remember we talked about Java Reentrant lock? They don't support lock upgrades. They only support lock downgrades. This allows you to upgrade, so you can upgrade yourself. If it's an optimistic read, then return the write stamp only if it's available. So again, turn it into a write stamp if there is a write, if there's nobody else using the write stamp. Otherwise, fail. And otherwise, if none of these other things hold, return a 0, which means I couldn't convert to a write lock. So that's upgrading. Now, of course, if you're already a write lock, it's not upgrading. It's just returning that you're a write lock. And you'll see how that gets used in our idiom here in a minute. The next thing is try to convert to read lock. So again, if you have a write lock, then you can downgrade it and give back a stamp that indicates a read lock. So that's downgrading. That's, again, done atomically. If it's already a read lock, return it, because you've got a read lock. And if it's an optimistic read lock, only give it the read lock stamp if nobody else has a read lock, because that's what it means to be optimistic. Otherwise, return 0. And then the final thing is try to convert to optimistic read. And if the stamp represents a lock, if it represents, let's see, if stamp represents holding a lock, release it and return. Oh, so if you have a lock, like if you have a read lock or a write lock, then go ahead and downgrade it to an optimistic lock and return what's called an observation stamp. If it's an optimistic read, return it if it's valid. Otherwise, return 0. Now, the final set of methods, and you can see there are a lot of methods here. These are ways to release locks. So you can explicitly release a lock to release a write lock. If you own a write lock, you can unlock it and say writer be released. Whoops, that should say unlock read. It's annoying. Fix that. Get back here. You can unlock a lock as a read lock, and then the final thing is just unlock. And this takes a look at the stamp, and it takes a look to see if the stamp is a read stamp or a write stamp, and it does the appropriate lock. So in theory, you could just call unlock all the time, but calling the specific things when you know what you have is a little faster and a little cleaner for the programmer who's trying to read the code. All right, let's take a look at some examples. A lot of this stuff doesn't make any sense until you actually see it get used. So this particular example comes from the documentation. And so if you take a look, you'll see this. I'm going to walk through it and give a more blow-by-blow description of what it's doing. So let's assume we have a point class, and the point class is going to have x and y, and that's the state that we want to protect. And then we have a stamped lock, and that's the guy that's going to actually do the protecting. And here's a method called move. So move needs to be exclusive. We're changing the state of point. So we're giving it new x and y. So we come down here, we acquire a write lock. Keep in mind this will block until it gets it. With the lock now held, we update x and y. And then finally, on the way out, we unlock the write lock. Now keep in mind, we could have said unlock stamp, not unlock write, and it would have figured out which one to do. But since we know what we're doing here, you might as well call unlock write, just because it's a lot more clear what's going on. It's probably a little faster too. OK, so that's move. That's an easy one. Here is a read-only method. So this method is trying to do a read. Now, of course, we could acquire for reading, right? We could just do a read lock, but we're going to demonstrate the use of optimistic reads. So we come in here, and we're going to try to get an observation stamp. So we call try optimistic read, and that'll return a stamp. And now what we do is we're going to be really optimistic. We're not even going to check the return value of this thing to see if it worked or not. We're going to go ahead and we're going to set local variables cur x and cur y to x and y, which are the current state of the point. Now, keep in mind, this is an optimistic read, so there were no locks held at this point. We just gave back a stamp that said, I'm an optimistic read stamp, or I'm an observation stamp. So what happens now is we have to go ahead and see, did anybody come along and try to change the state by acquiring the lock for writing? Now here's where there's an important difference between a library-based solution to something and a programming language-based solution to something. So in this particular case, we really don't know whether anybody changed x and y. All we know is that somebody might have acquired a write lock. Now it's a pretty darn good chance if they acquired the write lock, they changed x and y. But we don't really know that. We just have to surmise that. Whereas if you were actually building a programming language-based solution to this, you could actually put checks in the code to see what had happened to those values. That's a little safer, but it might also be more clunky too, for that matter. It might be slower in many ways. But the point is that we're going to assume that if validate succeeds, we're basically done, right? Nobody came along and updated this stuff, so we can use those values and not have to worry that they were corrupted. However, if validate returns false, that could mean that someone's come along and changed x and y while we were in the process of reading from them, which means that their values may be entirely garbage. In fact, they're doubles, right? So chances are they will be garbage if they were being changed at the same time. Or you might have gotten, if they were ints or something, one might be the right value, the other might be the wrong value. So the minute validate returns false, we don't know what the heck the state is. So in that case, what we're going to do is now we're going to say, OK, I'm being pessimistic, right? I started out being optimistic. The glass was half full. Now the glass is half empty. I'm just going to wait to get the read lock, get a real read lock. And then once I've got that, then I'm going to do the pessimistic reads, right? The lock is now held. I have shared access. I can do reads, but I will make sure that nobody can come along and do writes at the same time. And then on my way out, I unlock the read lock. Now, notice something interesting. If validate succeeds, we don't release anything. because we never acquired a lock in the first place. So there's no need to ever release an observation stamp because it didn't acquire anything in the first place. Validate does all you need to do, which has to do with cache management. And then once all this stuff is done, we've now got current x and current y, which are local variables to have the right value, and then we use them in our mathematical operation. And that computes the current x, current y at that point in time. Of course, the second that this thing gets called, somebody may have moved it again. But at that point, we had the right value, right? We didn't have inconsistent values. Any questions about that? So that's an interesting case. Yes, Jake?
At what point will this actually be more efficient than just going pessimistic from the get-go?
We'll see an example in a second. OK, now here is the third and most complicated case here. This is what's called a conditional write. OK, so we did an unconditional write, which was the move operation. Then we did the optimistic read. And now we're going to do move if at origin, right? So what we're going to do is we're going to come in here, and we're going to acquire the read lock. So we got a read lock. And now, while x equals 0 and y equals 0, right? So if we're at the origin, we're going to move, right? Now, this looks like a loop that may go a number of times. It's only going to execute twice. That's the max it'll ever execute. So the first thing we try to do is we try to convert the read lock into a write lock. So keep in mind, why do we need the read lock? What was the reason why we grabbed the read lock in the first place? Eugen.
You want to check the while loop, see if it's in the origin.
Right, so we want to check if x and y are 0. And we have to do that in a way that doesn't require any worry about the data going out of scope. Of course, we could also do optimistic reads and so on, but let's ignore those for a second. So we come in here. Now that we know there's 0, now we need to convert this thing to a write lock so we can go ahead and change their values, because we're going to move if they were at the origin, right? If and only if. So we try to convert to write lock. Now remember, try to convert to write lock will only return something that's non-zero if the write lock is immediately available. If the write lock is not immediately available, and we definitely don't have a write lock at this point, right? We have a read lock. This will fail. So if it didn't fail, in other words, if we got a write lock, then we can go ahead and update the state, right? And notice in this case, we also set stamp to the new stamp, the write stamp. So if we succeed, we convert without blocking. And then when we break out of the loop, by the way, we're not looping anymore, right? If that didn't work, right, if we weren't able to convert to a write lock, then we come along and we unlock the read lock so that there's no more readers. And then we're going to wait to get a write lock. Now, of course, this is very important. Why do we have to unlock the read first?
Because it's not a Reentrant lock.
It's not only not a Reentrant lock, but we're trying to get a write lock. So if we held the read lock, you can only become a writer when there's no readers. No readers that are currently active at that point. I think it's called no predecessor readers or something like that. No predecessors are on the queue. So now we're going to unlock the read lock, and then we're going to wait to get a write lock, and then we're going to loop back around again. So the second time through, we will now have a write lock, and if it equals 0, then we can go ahead and convert to write lock. And if it's not 0, we just bail out, right? So if the values are 0, then when we come back around again and try to convert to write lock, we are a write lock at that point. So that will guarantee to succeed, and then we go ahead and update the state. Yeah?
So try to convert doesn't actually lock, it just returns a log that could be.
All it does is it checks. So the stamp keeps some status information about what state it's in, and a version number as well, like a generation count. And so all these try to convert, try convert, blah, 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 they just go and look at the state. And they say, if you're trying to convert to a write lock and there's no readers or writers, you just say, here, you're a writer now, right? No need to lock. Or if you do lock, it's stuff like conditional test and set, that kind of stuff, real fast. But you're not going to block. That's the other thing I should mention, by the way. So I'll send a link out to this. Doug Lee has a really great tutorial where he talks about engineering concurrent library components. And I listened to it while I was out trimming the hedges this weekend. I'm like, I might as well do something, that'll build my brain while I do mindless yard work. And so I was listening to it. And one of the points he was making, which is really interesting, if you think about it, it's obvious. Processors can go really, really, really fast. You can do, gazillions of operations per second, right? But the minute you park something, the minute you block, then, tens of thousands, hundreds of thousands of cycles are just being wasted idly. So in modern multiprocessor optimization lore, you don't want to make things stop unless you absolutely have to. In fact, you'd prefer to spin a little bit if that'll make you keep making progress, because it's perfectly okay to spin a bit even if you're not doing anything useful, because putting yourself to sleep and parking yourself will waste so many cycles, you'd rather just spin. So if it's a question of spinning 10 times versus spinning for 10 cycles versus going to sleep and then waking up and wasting 100,000 cycles trying to go to sleep and wake up, you'll spin, right? So it's an okay thing to do. So a lot of the stuff you see in this implementation is really trying to be clever about not sleeping unless you absolutely have to. In fact, he also talks about work stealing algorithms that people use, so that if they don't have anything left to do, they look around to their peers' stuff and they do that stuff, just to keep things going. They'll take things off the end of queues, for example, which can be done very efficiently, just to keep doing something. It's like somebody who's got obsessive compulsive disorder and they got to do something, right? They got to work. Can't stop. Or people who drink too much coffee. So did that answer the question?
Yes.
Okay. So finally, when you're all done, you unlock the lock. And notice that you're either going to unlock the write lock or you're going to unlock the read lock, depending on what you found. And so we just do an unlock here, and it'll figure out which thing we've got, and it'll do the right kind of lock. So you're either unlocking a write lock or you're unlocking a read lock. Okay, let's talk a little bit about usage considerations. So here's a good benchmark. In fact, if you take a look at this link, you'll see lots and lots of stuff. I just picked one picture that was the most interesting one to me to make the point I was trying to make. But he actually sits there and goes through a whole bunch of different combinations of things. N readers and N writers, and lots of readers, lots of writers, and all this kind of stuff. And what he does is he compares synchronized locks, optimistic locks, which is the try optimistic lock thing we were just looking at, Reentrant read-write locks, and stamped locks that use reading and writing without being optimistic, right? And here's what he finds. So in this model, bigger numbers are bad, right? So that means it takes you longer to do the amount of computation you're trying to do. And what you find here in this particular example is that optimistic locks work really well, because for whatever the work conditions, they didn't have a lot of contention. So not locking when there was no writers meant you could zip through that critical section very quickly. Reentrant read-write locks are like an order of magnitude slower. Actually, 2 orders of magnitude slower, right? They're really slow. Stamped locks are better than Reentrant read-write locks. They're about half as much overhead. But then look, good old-fashioned synchronized, right? The good old granddaddy of everything that just comes built, in for free. That's way better than the reader-writer locks and the stamp locks without optimistic reads and writes. But optimistic reads and writes are about twice as fast as synchronized. Yeah?
The optimistic is the stamp lock with that idiom.
The try optimistic read thing, exactly. And this particular case, the reason why this works so well, if you look at the article, there's other cases where things behave differently. There's a lot of readers here and only a writer periodically. Now, obviously, if you have 19 readers that are reading when it's able to read, but you have one writer that just sits there continually writing, right, then you definitely should just go ahead and use a synchronized block, right? Because there's no reason you're not going to get any benefit from having readers-writers for the most part. They're never going to get a chance to read, or going to get an infrequent chance to read. And they're always going to have the optimistic locks invalidated, right? So that's why I said before, a lot of these things depend on the workload pattern that you're trying to use as to whether they're a win or not. All right, so that's the good thing. Often way faster if you know what you're doing. The downside is they're a lot more complicated to use. So first of all, there's just a lot more methods. So here's the public methods from Reentrant read-write lock. and here's the public methods for StampedLock. And you can see the reason for this is that there's all these different modes, right? There's write mode, read mode, optimistic mode, all the conversion operators, all the different unlocks, da-da-da-da-da, right? So there's just a lot more stuff. So there's more things to know. There's also much more complex semantics and usage patterns. You've got to understand how to write this conditional write type of operation code. And if you don't get this right, or if you do it in a way that doesn't actually benefit, you're not going to get a win, but your code will be a lot more complicated, right? In which case you're just better off using synchronized blocks or synchronized methods. And something else we talked about before, they're not reentrant. So as we said before, here's an example where you have some component and you have some method 1, and some method 1 acquires the lock for reading, calls some method 2 acquires the lock for reading. Oh, bad news. Not going to work right. Now, what will actually happen, I don't even know if they check for this, but it's bad. So they might just end up in a situation where it doesn't keep track of the number of times it's called. So the first time you call unlock, it unlocks them all, which is not what you want, right? You want to keep the counts coordinated. All right, this is where the source code is. We're not going to look at the source code right now. We'll come back and look at that later. It is really subtle code. It doesn't use abstract queued synchronizer, so that part, you don't have to learn all that part, but it's got a lot of really subtle stuff in it. And Doug Lee is a really good programmer, so it's done very well, but it's also somewhat obscure. If you listen to his webinar on YouTube, he says that on a lot of modern processors, if you spin and don't do anything, the processor thinks you're running the operating system's idle loop and powers down that computation to save power or not do work. So what they actually have to do is when they spin, they actually have to compute random numbers just to do something. And so they like XOR things together just to compute random numbers to fool the processor into thinking that it's not doing nothing.
Upgrade from coffee to Monster, now you really just have to do something.
Yes, that's right. You have to do something, yes. It's pretty funny. It's like Hermione Granger in Harry Potter. You've got to do something, right? You got to get a time turner and take all your classes. Take twice as many classes as everybody else. I just got done yesterday reading the very end of Chamber of Secrets to my son. And if you remember that story, at the end of it, Harry, of course, once again saves the day. Still entirely unclear to me why they even suspect him of ever being a bad guy, right? I mean, how many times has he saved everybody? But Hermione is woken up after being petrified, and she's disappointed because they've canceled exams, right? So, so she definitely is someone who would spin, not sleep, right? So you can see there's lots of stuff in here. We'll look at this later.